Swayam Prabha. Digital India. Educated India.
Hello everyone. So, in the last class we started deriving the compressible lens equations and we looked at the Power averaging. So, the Reynolds averaging was suitable for the incompressible lens because there was no variation in the density, but in the compressible flow we have to account for the variation in density also. So, the power averaging is, or the density weighted averaging is more suitable, and as you can see here that we can define this density averaging as let us say u tilde is equal to rho u bar by rho bar, where each on top and bottom are basically Reynolds averaging, this is density weighted average and thus the density average, right. And then when we use there we ultimately get two terms, okay, after taking the time mean of this entire thing, because rho v prime v double prime goes to 0, this goes to 0, u double prime goes to 0, and only these two terms are remaining, right. So, now let us use these equations and try to derive the Lorentz equations for the compressible flow. Okay. So, let us start with the continuity equation or the mass conservation equation. So, this is our mass conservation equation. In 3D it can be written as del rho by del t plus del rho u by del x plus del rho v by del y plus del rho w by del z equal to 0. Okay, this is the vectorial notation, or you can have in the vector notation if you want to write. Okay, that is del rho by del t plus del dot rho u will be 0, right. So, we will decompose these equations by considering the Reynolds averaging as well as Fowler averaging, okay, because ultimately you have to do the time averaging, but for the decomposition of different variables we will use different kind of averaging. For the density, okay, as we have given here, we will use the Reynolds averaging. So, rho equal to rho bar plus rho prime. For the pressure also we are going to use this Reynolds averaging, P equal to P bar plus P prime. For the velocity and the temperature we are going to use the Favre averaging. So, this will be Favre, okay, which is ui, all three velocity quantities can be given as ui tilde plus ui double prime and so on and so forth, and these are the typical Reynolds averaging. Okay. So, now use them on your continuity equation. Okay. So, let me work this out here. Rho is rho bar plus rho prime by delta t plus del by del xi. Okay. We have this rho bar plus rho prime, okay, and you can have u tilde plus u double prime is equal to 0, or what you can do is instead of doing this rho bar plus rho prime, just use this rho here, because anyway that will get cancelled out because you are using the Favre averaging, just keep it rho, okay, equal to 0, then take the time mean of the entire thing. Okay. So, this will become d rho bar by dt plus d by dt rho prime bar plus d by xi rho u tilde bar, and that will be del by del xi rho u double prime y equal to 0. Now, this is 0 by definition and this is 0 by definition. Remember, for the Reynolds averaging, the quantity that you have, the fluctuation of that goes to 0, the quantity is f, the f prime bar equal to 0. In the Favre averaging you have rho f double prime bar goes to 0, right. So, that is why this is rho u, this is going to 0 because this is multiplied by the density, right. So, then your equation becomes d rho bar by dt plus del by del xi rho bar u tilde equal to 0, and what is rho bar u tilde? Rho bar u tilde is equal to nothing but rho u bar, right. So, this can also be written as del rho by del t. Okay. So, I have just used this u, I mean for 1D, but you can also use I here. So, that will become for all the 3D, okay, plus del y del x I rho u I bar is equal to 0. Again the form is similar to the there will be rho bar also here. The form is similar to the continuity equation in the Navier-Stokes, except that now all the terms, all the variables are replaced by their averages. Okay. Now comes the momentum equation, right. So, this is the momentum equation form that I have written here. I have put everything on the left hand side. Okay. Now, if you look at this equation closely, right. So, this is the most problematic term that we have. Okay. Remember, we are using for the u and v and w, we are using the Favre averaging, okay, so on and so forth. For pressure and density, we are using the Reynolds averaging. So, if you use those relations, okay, so you can this is the only term that is going to create problem, other terms are self explanatory. So, you can basically take this rho u I, right. So, you can take this rho u I tilde plus u I double prime, right, and this rho u I double prime will go to 0. So, this the first term will be nothing but rho bar u I tilde by delta t. Okay. What will the second term? Just like what we had in the incompressible Navier-Stokes equations, we will have two terms here, okay, and there will be a term appearing which will be like the Reynolds stress as we had in the incompressible Navier-Stokes equations. So, if you recall the difference of Favre averaging, this will become rho bar u I tilde u j tilde, then it will become my, and this will be plus rho u I double prime u j double prime whole of bar, right. So, this is your Reynolds stress term that is appearing here, right. Pressure is nothing but P plus P prime. So, this will and then you are taking the mean of that. So, this will become P bar delta I j. Now, problem here, there is problem with the tau I j. Why is a problem? Because tau I j is basically proportional to the velocity gradient del u I by del x j, okay, and there is no rho multiplying here, right. So, you can write it as, so if you have this tau I j and it can be written as 2 mu S I j star, right, which is nothing but mu del u I by del x j plus del u j by del x I minus 2 by 3 delta I j del u k by del x k, right. This is what our momentum equation is. So, I am saying that now using for u, you are using u I is equal to u I tilde plus u I double prime, right, and then you are taking an average of that, right. So, what will happen here is that you will get the stress in terms of your Favre fluctuations, but what you are looking for is the in terms of Reynolds fluctuation, because your if you recall the incompressible equations, we had this yeah. So, you will have a Favre fluctuation, okay, Reynolds fluctuation we have already considered here, okay, the Favre fluctuation. So, you can write it the way to work out it there is basically write it as minus tau I j bar, okay, and plus there is another term which is coming because we are taking this u I double bar average, right. So, you have rho u by I sorry del, yeah. So, there will be a term which will be I call that tau I j L, okay, and that will be basically mu del u I double prime by del x j plus del u j double prime by del x j, okay, del x I, and minus 2 by 3 delta I j del u k double prime del x k, okay, and you are taking an average of that, okay. So, I am denoting all this as your tau I j L. So, you can write it as minus tau I j and minus tau I j L, right. Now, what is this tau I j L? Okay, this is stress in the fluctuation due to the viscosity, right. And what is this? This is the stress which is generated because of the turbulence, okay, in the fluctuations. This is because of the transport, and this is because of the viscosity. Generally, if you recall, we have been talking about that the turbulent viscosity is much higher, or basically the turbulent stress is generally much higher than the viscous stress. Further, this is the stress which is acting on the fluctuations, okay, Favre fluctuations, and not on the mean quantity, right. So, the mean quantity stress is given here. So, it has been found in many experiments, which is by I think Bremen and Gewitz. So, these they have basically found that this value, which is basically tau ijl, is basically very small compared to the value which is due to your turbulent fluctuations, right. So, you can neglect this term entirely, right. So, this term can be neglected entirely. So, what we have is basically now these 4 terms, okay. This is your viscous stress, or the stress due to the viscosity. This is your Reynolds stress, the turbulent stress, and these are the mean quantities as we had in the incompressible flow. And this term that which is appearing due to this tau ijl is basically it has been removed completely, okay, because this term has been neglected. Okay, so finally, that is our entire momentum equation. It looks very much close to the incompressible equation, and this term goes to 0. Okay. So, the additional term that we have is just we will call it Favre stress, maybe not Reynolds stress. Okay. So, you can denote it as tau ijf. So, the earlier we had denoted tau ijr, okay, or tau ij3, which is turbulent stress, which was basically now minus rho u prime v prime bar, and now we are denoting it as now tau ijf, which can be written as minus rho u prime v prime fluctuations, okay, rho bar u prime v. Okay, so this is your, or you can also write it as minus rho u double prime v double prime bar. Okay. So, this is my tau ijf. So, we have an additional fluctuation term. That is the only change we have in the momentum equation. Look at energy equation, and as you would expect that it becomes more complicated, because in this we not only have the pressure work, which is the interaction between the pressure and the velocity, but we also have this thermal conductivity term, okay, the thermal work, okay, rho u j e, and of course, the change in the energy with time. So, all these terms are there, but the philosophy remains the same, because we are using T is equal to T tilde plus T double prime. Okay, so, you will have additional terms appearing, let us say in this one, because first we will use this decompositions, all this decomposition e bar plus e prime, and so rho u. Okay. So, you will be using all these decompositions, and ultimately we are taking a time average of that. So, if you do that, what are the terms that we will be getting? Okay. So, the first term, as you would expect, it will become, so you have rho e, right. So, e, what is e? E has got 2 terms, which is the velocity, the CVT plus half rho u square, right. So, both this T and u, we are using the Favre fluctuations, right. So, Favre averaging. So, it can become T tilde and this u tilde square, right, something like this. Okay. Move the u here, because u square, right. So, C b equal to R T R by gamma minus 1, right. So, this is R T by gamma minus 1 plus half rho u square, right. So, if you have both the terms in the Favre fluctuations, so anything that is multiplied by rho into the Favre fluctuation goes to 0, right. Similarly, your rho T double prime will go to 0, right. So, these 2 term will go to 0. So, ultimately what will remain is only this term, right, or you can write it as rho E bar, both are same, right, where E consists of both the temperature as the velocity. Okay. In this, as we had expected, that you will have the work due to the turbulent stress. Okay. This is the turbulent stress term. Right. This is the pressure work, and this is the pressure work due to the fluctuations, and then you will have uh, this stress work, okay, that's tau I j into u j, and then you will have this finally you have the quantity which is q j, right. And this is again written in the detailed format. I will not go into a detailed discussion, okay, but there are some things that you need to basically see. This is your molecular diffusion, okay. Please go back and derive it. It's slightly complicated, but you can do it by considering all the decomposition that you have talked about, okay. And this is a kind of turbulent diffusion of heat. Right, or maybe call it turbulent transport of heat, not the diffusion. Okay, this is tau I j, not this is tau I j u j double prime, right. So, you can see now we have got some more additional terms. One is this term, okay, which is rho bar u I prime u j double prime tilde, and then you have these three terms, okay, which is coming due to the interaction of different terms, which is the heat and the stress with work and the density with the velocity. So, all these three terms are going. So, we have got 9 unknowns here, 6 unknowns here and 3 unknowns here. But what we can do, we can use some kind of Reynolds analogy, and we can relate those terms which are these terms in terms of your mean flow variable. We will discuss that when we come to the eddy viscosity model, okay. So, right now you can just see that we have got this term which is very close to the incompressible flow term, okay. In fact, analogous to the incompressible flow Reynolds stress term, this is the Fowler stress term, and we have some terms which are coming due to the fluctuations. Again, like what we had earlier is we had talked about some of the terms which can be neglected. Here also some of the terms which are related to the viscosity or the viscous diffusion of the fluctuations, they can be neglected, and this is the final expression of the closed form approximate equations after neglecting many terms, okay, which are related to the viscous diffusion of the fluctuations, okay. This is similar to our Navier-Stokes continuity equation, except that we have bar, okay. This is also closer to that equation, except that we have this Reynolds stress term coming here. So, this tau I j total is tau I j laminar plus tau I j turbulent, okay. And similarly here also. So, this is the pressure work, the transport of energy, the rate of change of energy, okay, and then you have this heat terms, okay. So, this is the q j total will also have basically the q j laminar and q j turbulent, okay. So, ultimately we have got these tau I j turbulent and q j turbulent that needs to be modeled, okay. So, this is how the different terms looks like. Tau I j laminar here, tau I j turbulent here, and tau I j laminar is nothing but 2 mu S I j star, okay. In case of laminar in compressible flow, it was 2 mu S I j, okay, and tau I j turbulent is basically rho bar u I double prime u j double prime, okay. This is the laminar, which is lambda is the thermal conductivity, so lambda del T by del x j, okay, and this is your turbulent flow, which is basically the turbulent transport of the heat, okay. This is Cp rho u j double prime T, and this is the approximation to that, okay. We will come to this later, but ultimately what we are saying is that it is somehow related to the diffusion quantity which is happening to the viscous flow, and you can relate this entire term in terms of a different Prandtl number or different conductivity, which is called lambda T, okay, which can be related to the turbulent Prandtl number. Remember this lambda, you remember the Prandtl number we had discussed earlier, this is mu Cp by lambda, we had used earlier at k. So, this lambda becomes mu Cp by Pr, and for the gas, for example air, the PR is equal to 0.7 or 0.71, and you know Cp, viscosity, you can calculate the conductivity. If you can use a similar analogy, because we are getting one additional term here, so we can use a similar analogy, and we defined another term which is lambda T. Okay, that will be mu T, Cp and PRT. Okay, this is now a turbulent Prandtl number, and mu T is basically the eddy viscosity or turbulent viscosity. So, I am jumping ahead little bit, but I will get back to these terms again when we talk about the eddy viscosity model. Okay, just to give you an idea, so what I am trying to say that my fluctuations minus rho bar u double prime v double prime tilde, which is what I call as tau ij f, or the Favre stress, or in fact in the Reynolds stress also, is somehow related proportional to your mean velocity gradient. Okay. Just like your tau ij laminar, okay, this term is related to your velocity gradient here, okay, del u by del x a. Similarly, somehow we can relate it the turbulent stress also to the velocity gradient. Okay, this is what is called the Bouguereau's hypothesis, and here the proportionality constant was mu, okay, the viscosity, and here we will coin a new term, okay, which is called the eddy viscosity, mu T. Okay, and once we got the mu T, we will also try to use this on mu T information to find our turbulent transport of heat. Okay, and we will coin another number which is called the turbulent Prandtl number. Okay, this is again modeling, and from the turbulent Prandtl number we will use this turbulent thermal conductivity lambda T, and that lambda T will determine our turbulent transport of heat. Okay, this is important for the energy equation. This was not there in the incompressible flow. Okay, so finally we got all our Rayleigh equations for the incompressible flow. For the compressible flow, we know that what are the terms that needs to be modeled, and now the question is how do we model them. Okay. So, like in the incompressible flow, we have got three normal stresses, u prime double prime square, v double prime square, and w double prime square. Okay, and we have got three independent shear stresses. So, it is a 9 by 9 tensor, 9 by 9 matrix, right. So, three which are the isotropic terms, which are normal stresses, they give you the turbulence kinetic energy, right. And then we have additional three terms which are the shear stresses, and they are symmetric here. Okay, so we have got 6 independent terms which needs to be found, and additionally we have the turbulent transport of heat, but that can be found if we use some kind of if you can find these things, because we will use the Reynolds analogy there. Okay, and finally we will define something called turbulence intensity. So, we will define this if you know the turbulence kinetic energy. Okay, we will say that my u double prime RMS, okay, root mean square velocity is, this is u double prime square plus v double prime square is w double prime square, the square root of all these things, okay, by 3, okay, and this is nothing but square root of, this is nothing but your kinetic energy 2 into k by 3. So, if you know the kinetic energy, turbulence kinetic energy, you can divide it by the mean flow. Okay, you know the RMS value, divide by the mean flow, and that will be your turbulence intensity. So, whenever you try to basically solve any turbulent flow problem, you need to know the turbulence intensity, right. So, you might be doing experiments in different wind tunnels, okay, and the different wind tunnels have may have different intensity. Okay, it can be very quiet tunnel, and your intensity, the turbulence intensity can be very low, maybe 1%, okay, 0.1%, 0.5%, or it can be a noisy tunnel where the intensity can be very high, maybe 5%, 10%, and so on. Okay. So, once you know the intensity, you can use that to basically use that in the model to find different terms, including the turbulence kinetic energy, dissipation rate, and hence the stresses. Okay. Now, before I finish, I just want to talk about the eddy viscosity model briefly. Okay, so now we know that we need to model the Reynolds systems. Okay, let us focus on that, and do not get confused between the compressible and incompressible, because ultimately we are looking for closure of the term in the incompressible, which is rho u prime v prime bar. Okay, in the compressible it is minus rho bar u double prime v double prime tilde. Okay, but both are analogous. Okay, this is Reynolds stress and this is the Fabre stress. Okay, tau I j r, tau j f. Okay, so we are looking for closure of this term. So one way is basically, if you want to get the value of this, okay, you can basically try getting a dynamical equation for this, right. So you will use, let us say now you have the equation for rho u in the momentum equation, you can use the equation for rho u v for example, okay, and you will get an equation for rho u prime v prime bar, okay, by subtracting the mean flow from there. Okay. Similarly, if you want to, let us say rho u square term, okay, so that will give you rho u prime square bar, right. So the top one will give you rho u bar v bar. So you will get in question which is del by del T of this plus the transport of this, and there will be something related to pressure, some related to your viscous stress, but then we will get a term which will have the components which is like rho u prime v prime, maybe you can say that w prime bar, or u prime v prime bar, or u prime v prime bar. So you started with the double correlation and you will end up a unknown term which is the triple correlation. Okay. Remember the turbulence is always 3 dimensional, right, you can have fluctuations in all the direction. So you are back to the same question, that how do we find these terms, right. Although you have delayed the approximation, instead of modeling it right here, you are modeling at very late, and you are trying to model, let us say the triple correlation or maybe the next order correlation, right. So this kind of approach where you try to get a transport equation for each of the stress term. So this is u prime v prime, but you will have to do it for u prime w prime bar, u prime v prime w prime bar, u prime square bar, v prime square bar, w prime square bar. So we will have 6 transport equations, 6 Reynolds stress, for the lack of better word, let us call it turbulent stress, which can basically do it for both Reynolds stress as well as Fabre stress. Reynolds stress transport equations. Okay, you derive these equations, and then you will get the triple correlations which are unknown. Okay, and you model them. Okay, so this is what we do in the model called the RSM model. Okay, Reynolds stress transport model, okay, or Reynolds stress model. The other approach is that as I just spoke a few minutes back, that you try to relate these stresses somehow to the mean flow gradient. And why do you do that is, remember the picture that discussed some time back. Okay, so what we have is like, if you have a layer like this, okay, and you have the mean flow, and then you also have the eddies, which is like this, right. I think I discussed in the last class, right. So these eddies are also related somehow to the mean flow gradient. So what if you take any two layer, okay, like this, and take an eddy. So what is happening, that any transport in the fluctuation is happening due to this mean flow gradient. So it is happening in the direction of the gradient. So if the gradient you have higher velocity on the top, okay, and the lower velocity at the bottom, okay, so in that direction the transport is happening, the momentum is getting transported, right. So considering that picture, what we can say, that my Reynolds system, or the the Fabry stress term is also related to the mean flow gradient. So, I will say that my rho u prime v prime bar is also proportional to the mean flow gradient. Okay. In this case, is the del u bar by del y. Right. If you make that assumption, okay, then the life becomes very, very simple, because right now I am talking about only u prime v prime bar, but that you can take different flow components in the 3-dimensional flow, and the only thing that you need to determine is the proportionality constant. Okay, how is it related to the mean flow gradient? And that proportionality constant is usually termed in the literature as the eddy viscosity or the turbulent viscosity. So, this is minus rho u prime v prime bar is equal to mu t del u bar by del y. Okay. And this so we had 6 unknowns, okay, and we actually changed all the unknowns to just one variable, which is mu t. Okay. So, if you could somehow find this mu t, which is the eddy viscosity, or also called turbulent viscosity, we will be able to find the stress term, and by using the Reynolds analogy, we can also find the turbulent transport of heat in the compressible flow equation, energy equation, right. So, this is the only variable that we need to somehow model, and that is what we do in most of the turbulence model which are popular today. This kind of approach is called the eddy viscosity model, okay, which is different from the turbulent transport model that we discuss here, RSM model. Okay. So, all the equations that you see, k epsilon, k omega, SST k omega, even QB k epsilon, EARSM, all those kind of models are basically trying to find this eddy viscosity. The QB k epsilon and EARSM model, they are, see here I am saying that proportionality constant is linearly related, but you can also say that it is related quadratically or cubically to the velocity gradient to make it more approximate. So, those are like QB k epsilon or ARSM, they are those kind of models, even V2 omega, either those kind of models. So, ultimately we have to find that eddy viscosity, okay, and we have reduced our problem to a single unknown, and we will see in the next class that how what are the different eddy viscosity models, how do we use them. We will look at first the 0 equation model, 1 equation model, 2 equation model, and so on and so forth. We will also generalize it for the 3-dimensional flow. Okay, right now I am only looking at the picture which is a sphere, but we will generalize it to 3-dimensional flow. Okay. So, see you in the next class. Thank you.